Hi Bobcats. When we wrote electron configurations in the last video, some of those electron configurations got to be really long, like iridium with its 77 electrons. So what we'd like to do in this video is come up with a shortcut for writing those electron configurations. The shortcut that we are going to develop here is going to use the concept of a noble gas core. The noble gases, which are that last column, column 18 in the periodic table, are elements that really don't react, and they don't react because their electrons are arranged in a very stable arrangement. And so it's usually the electrons beyond that noble gas core that are available to participate in an electron's chemistry. And so those are the ones we're really interested in. So we can use a noble gas core shortcut to write an electron configuration for an atom and still see all of the electrons that we are most interested in. So this noble gas abbreviation it gives us a quick and easy way to write the electron configuration. And just as an example, I pulled up iridium, which is the long one that we did in the last video. And what I'd like to show here with iridium is how we can write a much shorter version that still shows all of the electrons we usually want to know about. So this line right here is showing us that full electron configuration for iridium. And if you go all the way out to 5p6, which is all the way out to here, those electrons in that pattern are arranged exactly the same way that the electrons are arranged in the element xenon. That particular arrangement is very stable because neon is a noble gas. So those electrons really aren't going to participate in the chemistry of iridium, so we can hide them and still see all of the elements that are likely to do anything chemistry-wise with iridium. So in place of this really long string of orbitals and electrons, we can simply write square brackets around xenon. And this symbol, the square brackets around xenon, means 1s2, 2s2, 2p6, and so on, all the way up to 5p6. So we can rewrite iridium's electron configuration this way, so that it is iridium's configuration is xenon 6s2 4f14 5d7. And note that these electrons that are coming after the noble gas core are exactly the same as we wrote at the end of the full electron configuration. Well, it's nice that we can write a shorter version, but it doesn't help us much unless there's a quick and easy way to get to that shorter version. And so that's what we're going to look at here with this slide. First of all, let's figure out what the noble gas core is for any particular element. So if you would look at your periodic table and find iridium there at atomic number 77, then what I'd like for you to do is slide all the way to the right where the noble gases are in the periodic table, and you will see that it's on the same row as radon. Radon is not our noble gas core. We have to go up one row to find it, which puts us at xenon. The noble gas core has to have fewer electrons than the element for which we are writing the configuration. So that's why we have to move up one row. So for any element, to find its noble gas core, all you have to do is find the element on the table, slide all the way over to the right, and then up one row. That's the element we're going to put in square brackets at the start of the configuration. So for instance, with iridium having xenon as its configuration, xenon in square brackets stands for the first 54 electrons in the electron configuration. So then we just continue following the pattern from the periodic table to fill in the rest. So electrons 55 and 56, for instance, fall over there in the S block, and that will be on the 6th row, so it'll be 6s2, and we just keep going from there until we finish the electron configuration. On this slide, I'd like to work examples of writing this shortcut electron configuration for 3 different elements. Let's start by practicing finding the noble gas core. So let's write the noble gas core for each one of these 3 first. So first of all, find oxygen on the periodic table. Oxygen's atomic number 8. To find its noble gas core, we're going to slide all the way over to the right and up 1, which puts us at helium. So the noble gas core for oxygen will be helium, and I will put that in square brackets. For cobalt, cobalt is atomic number 27. To find its noble gas core, slide all the way over to the right and up 1, which puts us at argon. So for cobalt's noble gas core, we'll write square brackets and argon. And then last but not least, we have tin. Tin is atomic number 50. To find its noble gas core, slide all the way over and up 1, and that puts us at krypton. So krypton in square brackets for its noble gas core. All right, so now to complete the rest of the electron configuration, we just follow the pattern from the periodic table. So for instance, with oxygen, oxygen has 8 electrons, helium only has 2. So that means we need to write in an additional 6 electrons. So electrons 1 and 2 are already taken care of by writing HE in square brackets. Electrons 3 and 4, that's just counting up from helium over towards oxygen. Electrons 3 and 4 are on the second row of the table in the S block, so we'll write 2s and we'll completely fill that subshell. To get over to electrons 5, 6, 7, and 8, they are on the second row in the P block, so we'll write 2p, and 5, 6, 7, and 8, that's 4 electrons. So oxygen's shortcut electron configuration is 2s2, 2p4. Another way of thinking about getting the 4 is once you get to that last subshell, which we know is 2p, you just count over from the left edge how many elements you have to go until you get to the element you're writing for. So in this case, that left edge starts at boron, and we just count over to where at oxygen, starting with 1 for boron. So 1, 2, 3, 4. That puts me at oxygen, so I know that exponent needs to be 4. Now for cobalt, with its 27 electrons, the symbol argon in square brackets accounts for the first 18 electrons. So counting up from 18, electrons 19 and 20 are in the S block on the 4th row, so that will be 4s, and we'll put the 2 for electrons 19 and 20. And then when we move to the next subshell, that's in the D block, so we'll use 1 less than the row number, so it'll be 3d. And if I count over from scandium to cobalt, that's 1, 2, 3, 4, 5, 6, 7, so the exponent here will be a 7. For tin, the krypton in square brackets accounts for 36 electrons. Next, as I move through the atomic numbers, 37 and 38 are in the S block in the 5th row, so that's 5s2. And then we jump down to the D block, so that'll be 4d. And we're going to completely move through the D block, so that's electrons 39 through 48. That completely fills the D subshell with 10 electrons. And then the next block we hit is the P block. On the P block, we use the row number, so it'll be 5p. And to count over to 10, we count 2 places, 1, 2, and so it's 5p2. So to write this shorter noble gas core version of an atom's electron configuration, we need to first figure out what element is the noble gas core, and then add in all of the electrons past the noble gas core until we've built up to our target element.